All right, welcome back to the second semester. We start here with chapter 7, rational functions. Um, and by definition, a rational function is one in which you have a polynomial in the numerator and a polynomial in the denominator. And so notice we have a monomial over a monomial. Both of those are polynomials. So this is our parent function for our rational functions. And today we're going to be looking at graphing these with in some different formats. But let's start here again as a quick review with our parent function. The domain is going to be all real numbers, except x is not allowed to equal 0, right? Because we can't divide by 0. And as it turns out, our range is also all real numbers, but y cannot equal 0. And so since I'm not allowed to substitute 0 for x, that means I have no y-intercept. And because y does not equal 0, there's no x-intercept, right? If I substitute 0 for f of x here, right, there is no value I can substitute in the numerator to get 0. If we cross multiply, 0 times x is 0. We get 0 equals 1, which we know is not true. So algebraically, we can support the fact that there is no y-intercept there. The rational functions, one of the characteristics of the graphs is that they have asymptotes. And so here we have a vertical asymptote. Here x is not allowed to equal 0, so x is 0. And I know difficult to see there, but the y-axis is an asymptote. And then we have a horizontal asymptote at y equals 0, which is the x-axis. And in general, we have two branches, and the graph will look something like that. And then on this end, we have that. So there's our parent graph. And so now let's look at some transformations. Okay, so here, the first one we're going to look at, f of x equals 2 over x minus 2 minus 1. And then, so we go back to many of the functions that we've done this year, all the way back to parabolas and into absolute value and whatnot, in that we could rewrite this as a over x minus h plus k, just like we did with parabolas and others. So here's our h. So this is going to move the graph 2 units to the right, and this is going to move the graph 1 unit down. This would be our k value. So that gives us some information about asymptotes, right? So there's our h, there's our k. And we also know if I were to substitute 2 into the function, we get 2 over 2 minus 1, 2 over 0. That's undefined. And so that tells us that 2 is not in the domain. That also tells us that we have a vertical asymptote because we have a non-zero number divided by 0. So we'll write all these down here in a second. And so there's our vertical asymptote at x equals 2. And this minus 1 moves the graph down 1. So y equals 1 is our vertical or horizontal asymptote, rather. All right, so looking at some of the things they want us to go through, domain I'm going to do here. All real numbers, but x is not allowed to equal 2. Our range is all real numbers. Y is not allowed to equal 1. So we've got domain and range out of the way. We'll look at our asymptotes. So our vertical asymptote, we've identified at x equals 2. Our horizontal asymptote, we've identified at y equals 1. So that takes care of those. For wholes, remember we've talked about that if you substitute a number into the function and we get 0 in the numerator, 0 in the denominator, that gives us a whole. So there is no value there because we have a constant in the numerator. So there's no wholes. And that leaves us with x-intercepts. We should have y-intercepts here as well. And so for a y-intercept, right? If I substitute 0 for x, f of 0, 2 over 0 minus 2 minus 1. 2 divided by negative 2 is negative 1. So we have 0, negative 2. And then for an x-intercept, we're going to substitute 0 for f of x. I'll add 1 to both sides. I'll cross multiply. X minus 1 equals 2. And we get x equals 3. I feel like there's a mistake there. Oh, there's the mistake. It should be x minus 2. I don't know why I changed that there. So that should be x minus 2. So x equals 4. And so now, having our x and y intercepts, we have some points that we can use to graph. So the y-intercept is here at 0, negative 2. Our x-intercept at 4. And we know we have these two branches. We're going to approach these asymptotes just like Pinocchio told us, or Jiminy Cricket rather. Let your asymptotes be your guide. And there's our graph. Okay. Let's look at a second one where our format is a little different. Now, we can always change the format into this one by doing some division, but I don't know that that's always necessary or always helpful. So, but what I do want to do in terms of trying to figure out all the information is simplify this a little bit. And so I'm going to factor the numerator and denominator. So I can factor a 2 out of the numerator, and I get x plus 3. In the denominator, I can first factor out an x, and then notice I'm left with a difference of squares. And so that factors to x minus 3, x plus 3. So now notice we have a factor in common between the numerator and denominator, x plus 3. What that also tells us is that if I were to substitute negative 3 into this function, right, this factor in the numerator becomes 0, so 0 times 2 is 0. This factor becomes 0, and regardless of what those two factors are, 0 times anything is 0. And so this tells us that there is a hole at x equals negative 3, and we'll talk about finding the y value here in a minute. So in simplifying this, we can divide out the x plus 3's because that equals 1. And so our function is now 2 over x times x minus 3. And we want to add that provided x does not equal negative 3. And so to find the y value for the whole, we're actually going to substitute negative 3 into what's remaining. So negative 3 minus 3 is negative 6 times negative 3 is 18. 2 over 18 is 1/9. And that would be the y value where the hole is. Okay, so let's go through what we need. So we did find the hole. I'll list that a little bit later. So first I'm going to do domain. It doesn't list range here, but we're going to talk about that here in a second. So our domain, I'll put that over here, is going to be all real numbers except for any number that makes the denominator 0. And so that is negative 3, 0, right? Because if I substitute 0 for x, we're going to get 0, or positive 3. Okay, for our range, when we're in this form, and this is where we'll find our, well, we'll come to the range a little bit later. Let's do that. Let's do the graph, and let's do some other things first. So we've talked about the hole. So I'm going to cross up to me. I'm going to cross off hole. The hole is at negative 3 and 1/9. And so for vertical asymptotes, any value now that makes the denominator 0 but not the numerator will give us a vertical asymptote. So notice if I substitute 0, we're going to get 2 over 0. And if I substitute 3 for x, we'll also get 2 over 0. So x equals 0 and x equals 3. So we can cross that one off. Now, for horizontal asymptotes, remember we've talked about comparing the degree of the numerator to the degree of the denominator. Because horizontal asymptotes is really the end behavior, which is the limit as x approaches positive and negative infinity. And so when I substitute infinitely large or small values, that really is what our horizontal asymptote will be. What are we approaching? What is the y value approaching? And so if the degree of the denominator is greater than the numerator, then what's going to happen is the denominator will get bigger much faster than the numerator. So overall, the value would get closer and closer to 0. Because if I substitute a trillion, right, even though 2 times a trillion plus 6 is a very big number, divide that by a trillion cubed minus 9 times a trillion, that number on the numerator becomes much smaller comparatively, and then the whole thing gets closer to 0. So our horizontal asymptote will be y equals 0. If the degrees were the same, then it's the ratio of the leading coefficients. And if the degree of the numerator is greater, then the function goes off to infinity. There is no horizontal asymptote. There is potentials for other types, which we'll talk about much later. Okay, so we've done horizontal asymptote. Let's talk about x-intercepts. So I go back again to our simplified function. And if I substitute 0 for f of x, or 0 for y, again, remember, whatever makes the numerator 0 and not the denominator would make this 0. But because we have a constant in the numerator, there is no x-intercept. There's nothing that would make that equal to 0. Right? And if we did cross multiply, 0 times all of this would be 0, and 0 does not equal 2. For the y-intercept, and we'll substitute 0 in for x, so 2 over 0 times 0 minus 3, and notice again, right, we would get a number over 0, and that's also confirmed in the fact that we said our vertical asymptote was at 0, and the domain cannot equal 0. So hopefully you would have figured that out, that we didn't need to even do that portion. Okay, so let's see. Let's put in some of the things we know in our graph. Vertical asymptote, again, hard to see when it's the axes, but we've got to put that in there. That's x equals 0. We also have x equals 3. And we have a horizontal asymptote at y equals 0. Again, an axis. Okay, so now what we need to do is figure out where within these areas do we have a graph. Well, we know that we have a hole at -3 1/9. So -3, positive 1/9. So that would be right about there. And we know we never cross the x-axis, and we have to approach these asymptotes. So again, using our advice from Jiminy Cricket, letting your asymptotes be your guide. Okay, we know we have that. Now, in general, when you look at the pattern of rational functions, we know that we're going to have almost always a graph here and then a graph up here. But what we can do is we can test a point, because again, we know we don't cross the x-axis. So if I pick a point between 0 and 3 and plug it into the function, let's say 2, right, going back to here, 2 over 2 minus 3. Well, 2 minus 3 is -1, times 2 we get -2, so we have -1. So we know with 2 it's at -1, and we know we don't cross, so we know the graph has to look something like that. And if I substitute a number greater than 3, so a number up in this area in terms of our x-axis, or x values, if I plug in 4, right, that's 1. So at 4, we're at 1, and again, we know we don't cross the x-axis. So our graph would look like that. Okay, so now when we think about our range, right, what are our y values? We look at horizontal asymptotes in holes. Well, we know, we can start with all real numbers, y cannot equal. Well, we know we don't have 0, and an initial thought may be that we don't have 1/9. But we can see that on the other side here, we would have 1/9 as a y value for a positive x over here. So it's only going to be y does not equal 0. All right, I hope that helps. There is a lot going on there. A lot of good mathematics in graphing rational functions. And hope this helps. Talk to you soon.